Okay, I think it's working now. All right, so we're going to continue talking about the IEEE 754 floating point specification here, and so we talked about this on Monday, and then and we said in R we've got double precision floating point, which is which uses 1 bit for the sign, 11 bits for the exponent, and 52 bits for the mantissa, okay? And what we're going to do is we are going to use a mini float system where we have 1 bit for the sign, 3 bits for the exponent, and 4 bits for the mantissa. This is going to be kind of a parallel version of this, but this will be like super low floating point precision, okay? So, but it's the same kind of system that we're going to have, right? The sign bit is 0 or 1, 0 if it's positive, 1 if it's negative, okay? We've got 3 bits for the exponent, which means we have 8 unique values, and with that we implement an exponent bias so that we can represent both negative and positive exponents, okay? So with 8 values, half of them are positive, and then the other half are negative. So we have a exponent bias of 3, okay? And then for double precision floating point, we have 11 bits, so you can represent 2048 unique values, and you're going to have a bias shift of half of that, basically 1023, 1 less than half of that. And then for the mantissa bits, we have 4 bits for the mantissa, which means we can represent we're going to have basically those 4 bits follow a leading 1, because in normalized binary scientific notation, the leading digit cannot be a 0. It has to be something other than 0, which for binary is always going to be a 1. So we can always assume it's a 1. Okay? All right. Here's an exercise. What does this number represent? Okay? You might have to use a little bit of paper to figure this out, okay? Take half a minute here to work through this. 1 bit for the sign, 3 bits for the exponent, 4 bits for the mantissa. All right, well, let's just tell me, what is the exponent? What does the exponent bits represent? So what are the exponent bits? Which the 3 bits for the exponent are 0, 1, 0. Okay, and so with the bias, this is going to represent the exponent of. With the bias, it will be -1, okay? So here, let's talk through this, right? So the sign bit is the first bit, that's a 1. So we know this value is going to be negative, okay? The exponent bits are 0, 1, 0, which translates to 2, okay? But we have an exponent bias of 3, right? Is that all right? So, we covered that on Monday, but just reminding you, when we have 3 bits, we can represent 8 unique values. Half of 8 is 4, and 4 minus 1 is 3. So our exponent bias is 3. Okay? So the exponent is going to be 2 minus 3, which is -1. The mantissa bits are the last 4, 1, 0, 1, 0. Okay? And with a leading 1, that's going to be 1.1010. Okay? And this is negative, and we multiply it by 2 to the -1. We raise it to the exponent, and so we're going to get 1, the leading 1, and then the first spot after the binary point is 1/2. The next is 0, that's the quarters position. The next is the 1/8ths position, and we have 1 of those. So we got 1 plus 1/2 plus 1/8, and no 16ths. We multiply that by 2 to the -1, or we multiply that by 1/2. This adds up to -13/8, and we get times 1/2, and we get -13/16. And so this number represents -0.8125. And then if I swap this first bit to a 0, then it would just become positive 0.8125, okay, or positive 13/16. Yeah.
How do you know what the bias is?
How do you know what the bias is? So you say how many bits represent the exponent, okay, and you say how many unique values can I represent with that, and you take half of that because you want basically half positive, half negative, and then you subtract 1 from that. Okay, so with 3 bits, right? So I have 3 exponent bits. I can represent 2 to the 3, 8 unique values, right? Okay, and I want half of those to be positive and half to be negative.
Oh, okay.
Okay, so I'm going to do 8 divided by 2, which is 4. Okay, but then the engineers decided, you know, because there's a 0 and we use up 1, we're going to use 1 less than 4, so we use a bias of 3.
Okay, so for 4 bits, it's 7?
Yes, so for 4 bits, you can represent 16 unique values. Half of that is 8, and 1 less than that is 7. So the bias would be 7. So for 4 bits, you would have a bias of 7. And then for 11 bits, you can represent 2,048 unique values. Half of that is 1,024, and 1 less than that is 1,023. So the bias for 11 bits, which is double precision, is 1,023. Okay.
You subtract the exponent from the bias?
You subtract the bias from the exponent. Yeah. Yes. Yes. All right. Okay. So the solution. Okay. Another way we could have done this. So here I converted all of this to 1 plus 1/2 plus 1/8, and I multiplied that by 1/2. Another way I could have done this is I said, well, this is 2 to the negative 1, and I could roll that binary point forward, just like in scientific notation, you can roll it to the left or to the right based on it being positive or negative. And then we have 1/2, 1/4, and 1/16, and that adds up to the exact same value. Okay, so both ways to do it. Okay, so if we have this though, all right, what number would these bits represent? Okay, I've got 0 for the sign, 0, 0, 0 for the exponent, and 0, 0, 0, 0 for the mantissa. Okay, intuitively, we feel like this should represent 0. Okay, but with our current system, what happens is that we're always assuming that the leading digit is a 1, right? So here, with our current system, the exponent bits are 0, 0, 0. Okay, so with the bias, the exponent would be -3. The mantissa bits are 0, 0, 0, 0. And with the leading 1, that becomes 1.000, right? So that becomes 1 times 2 to the -3, or 1/8, okay, 0.125, okay? So this is a little bit like, you feel like it should be 0, okay? And with the current system, it doesn't work, right? And so this is why we have to introduce denormalized mode, okay? So assuming that the mantissa bits always have a leading 1 is useful, okay? It's useful because it reduces redundancy, because that is true for almost all situations, with the exception of 0, right? Anytime, if you've got a number and it's in normalized scientific notation, it's going to have a number other than 0 leading, okay? But if there's always a leading 1, there's no way to represent the value 0, okay? So we have denormalized mode, okay? And this is when the exponent bits are all 0, the digit in the front of the mantissa bits is going to be 0, okay? So normally we assume it's always 1, but in denormalized mode, that leading digit is going to be a 0, okay? Meaning it is no longer normalized scientific notation, and that's why we call it denormalized. Okay, and what also happens is that the exponent bias becomes 1 less than usual, right? So, this is to prevent some kind of discontinuity here, all right? And so normally our exponent bias is 3, but in denormalized mode, it's 1 less than normal. Our exponent bias becomes 2. Is that all right? Okay, so in double precision, our exponent bias is usually 1,023, but in denormalized mode, it becomes 1,022, okay? All right, so if we revisit this case of all zeros, then the exponent bits are all 0, okay? But we are in denormalized mode. Our bias is less than usual, 1 less than usual, so we're gonna have 2, and with a bias of 2, the exponent is gonna be 0, -2, or -2. Okay, the mantissa bits are all 0. The leading digit is 0 in denormalized mode. So this becomes 0.0000000 0, 0, 0, 0 times 2 to the negative 2, which is just 0, okay? So having all 0 bits represents the number 0, which makes sense for us, okay? And we're going to have two representations of 0. We got positive 0 and negative 0, right? And those are, most computer systems recognize those as entirely equal, okay? But I mean, I guess you can think of it as 0 approaching from the right and 0 approaching from the left, if you need to have some mathematical interpretation, right? Okay, and then we also have another special exponent case, okay? When the exponent is all ones, it has a special meaning, okay? It's either going to be infinity or not a number, okay? Infinity is the sign bit is 0 for positive infinity or 1 for negative infinity. The exponent bits are all 1, okay? Whether it's the mini float or the full double precision floating point. And the mantissa bits are all 0. Okay, so if you have exponent bits all 1, mantissa bits all 0, that's going to be infinity. Okay, not a number is going to be exponent bits all 1, and you have anything other than all 0. Any combination of bits other than all 0 will be not a number. So you have a whole bunch of ways to represent not a number using bits. Okay. And so one thing to note is that not a number is always going to be type double, okay? Because it's there's no nan for integers, okay? Nan only exists as a type double thing, all right? And this is true for other languages as well. So in Python, if you want to represent a missing value, generally you have to kind of convert it into double type, okay? Type, I guess type float in Python, and you can use nans. Okay, but there's no nan for integers. Although Python implements, they have an objects type which allows for nans for character type things. Okay. All right, so this would be the smallest non-zero value that we can represent. All right, what is this? What is this? What fractional number is this? All right, so let me just start you off. The exponent bits are all 0, which means we are in denormalized mode. So our bias is 1 less than usual of 2, so the exponent is negative 2. Then the mantissa bits are 0, 0, 0, 1. The leading digit is 0, so this becomes 0.0001 in base 2 times 2 to the negative 2. So what is this? 0, 0, 0, 1. So this is halves, quarters, eighths, sixteenths. I've got 1/16 times 2 to the negative 2. 1/64, right? So I got 1/16 times 2 to the negative 2. 2 to the negative 2 is 1/4. 1/16 times 1/4 is 1/64. Is that all right? Okay. All right, so then what's the next smallest value that we could represent then?
1 to the 32nd.
Yep, it'll be 2/64 or 1/32, okay? So the next value will be, in counting, so we got this, and then the next value will be 1, 0, okay? So again, our exponent is 2 to the negative 2. This is 0, 0, 1, 0, okay? So that becomes 1/8. 1/8 times 1/4. 1/8 times 2 to the negative 2. 1/8 times 1/4 is 1/32, or 2/64, okay? So we are incrementing from 1/64 to 2/64, or 1/32. Okay, so the increment between the smallest and second smallest values is 1/64. Okay, so a few more of these denormalized values. This would be 3/64, 4/64, 5/64, 6/64. Okay, and the increment between these values is 1/64. All right, what would be the largest denormalized value that we can represent? So I'm using 4 bits in the mantissa. What is the largest number you can represent with 4 bits? Okay, with 4 bits, you can represent 16 unique values, and the largest value you can represent is 15, because you get 0 through 15. Those are your 16 unique values that you can represent with 4 bits. So the largest value we can represent is going to be, in denormalized mode, is these are all zeros. I've got 1, 1, 1, 1, okay? And this is equivalent to, 1/2, 1/4, 1/8, 1/16 times 1/4. This is 15 16ths times 1/4. This is going to be 15 64ths. Does that kind of make sense? All right. Okay. What will be the smallest normalized value that I can represent? So what would the next thing be, right? So the next smallest value I can represent after this is kind of like the odometer changing. You've got 1, 1, 1, 1, and if you add 1 to this, it's going to roll up to 16, right? It's going from like 9999 to like 1000, so that's like exciting, but it's going from 15 to 16 in terms of binary, right? So it goes 1, 1, 1, 1, we add 1, and this becomes a 1, right? So this is that, okay? And this becomes 1, so now we're in normalized mode, regular normal mode, okay? Our bias is 3, okay? And so my exponent is 1 minus 3, my exponent is still negative 2. Okay, my exponent is still negative 2. The mantissa bits are all 0, and now the leading digit is 1, as usual, because this is now normalized mode. So I've got 1.000 times 2 to the negative 2, and that's equal to 1/4, or 16 64ths, okay? So we're still incrementing by 60 64ths here, all right? Okay, the next value here, I would increment by 1 here, all right? And then this just becomes 17 64ths. All right, so I have 1 plus 1/16, right? So I've got a leading 1. This is 1/16 times 1/4 gives me 17 64ths, okay? And so just continuing on, this would be 18 64ths, 19 64ths, 20 64ths, 21, 22 64ths, okay? All right, what would be the largest value I can represent where my exponent is 0, 0, 1? So it would be 0, 0, 1, and then this would be 1, 1, 1, 1. So what do you think? Okay, so this is what we get. We get, so our exponent is still 0, 0, 1. The others are 1, 1, 1, 1, okay? So this becomes 1 plus 15 16ths, right? So the 1, 1, 1, 1 is basically 15 16ths, okay? So I've got 1 plus 15 16ths. My exponent is still negative 2, right? So this becomes 31 16ths times 1/4, or 31 64ths. So we're just shy of 1/2. 1/2 would be 32 64ths, but here we're at 31 64ths. And so we're still incrementing by 64ths, okay? And we've gotten up to 31 64ths, okay? And then so the next value here, again, this is, again, think of the odometer, but in binary. And now if I add 1 to this, it just counts up to here, right? A 1, and then everything resets to 0, okay? So this is like reaching 100,000 miles on your car's odometer, okay? 99999, you add 1 and it becomes 100,000, and this is basically what we have now, okay? 100,000 binary is only like, what is that, 32 or something, 64? Okay, so I guess 32. And so the exponent bits are 0, 1, 0, which represents 2, and the mantissa bits are this, and the leading digit is 1, and so we are at 32 64ths. Okay, so this is an interesting thing. If you think of what this number represents in binary, what does this number represent? It represents 32, okay, right? So this is 1s, 2s, 4s, 8s, 16s, 32, and we're at 32 64ths, okay? If we kind of roll back, what does this number represent? This is 16, and we're at 16 64ths, right? And basically up to this point, we've been counting up by 64ths, right? It's just like take this binary and then just put it over 64, okay? And so we're here, and then we're at 31/64. Here we're at 32/64. But here is the amazing thing, okay? So here I'm at 32/64, okay? And now, what happens is when I add 1, instead of becoming 33/64, this is where the magic of floating point comes in, is that now we're going to take bigger steps, okay? Because if I kept doing this, with all of these bits that I have here, I would only, if every single increment represented 1/64, okay, this would be 32/64, and then I could represent 64/64, and then 128/64. The biggest possible number I could represent would be 2, okay, 128, or I guess not 2, it would be 250, 128, it would be like 363/64, okay, just shy of 4, okay? But this is where floating point, the magic of it comes in, is that once I'm here, these increments are now worth 1/32, okay? So what happens is this exponent bit is 0, 1, 0, which represents 2. Our bias is 3, okay? And so the exponent is now only -1, okay? Our exponent is now only -1. The mantissa bits are 0, 0, 0, 1, okay? Which means the leading digit is 1. Okay, so this becomes 1 and 1/16, or 17/16, times 1/2 becomes 17/32, okay? And so my increment goes from 1/2 to 17/32, okay? Or my increment is 1/32, okay? So rather than going up to 33/64, which so far we've just been kind of counting by 64ths, okay? We get to 32/64, but rather than going up to 33/64, now I'm taking steps twice as big. I'm going up to 34/64, okay? I'm taking steps of 1/32, okay? And every single increment here is now in 30 seconds. So if I roll this forward, okay, this is now 18/32, okay? And so a whole bunch of these, this is 18/32, 19/32, 20, 21, 22, 30 seconds. Each of the increments here are 30 seconds. The largest value here will be this, which will be 31/32, okay? So 0, 1, 0, 1, 1, 1, 1, okay? And then the next value will be 0, 1, 1, 0, 0, 0, and this will be equal to 1, okay? Here the exponent bits are 0, 1, 1, which is 3. With a bias of 3, this exponent is 0, and so I have 1.000 times 2 to the 0. This is equal to 1, or 32/32, okay? And now that my exponent is 0, 1, 1, each increment here is no longer a 32nd, but each increment is going to be a 16th, okay? So this thing, 0, 0, 1, okay, now represents 17/16, okay? So representing a whole bunch of this is 1, 17/16, 18/16, 19/16, and this keeps going up until we reach 31/16, okay? And then the next value would be what? After 31/16, we would have 32/16, and that's 2. Okay, so the next value is 2, and now the increments are 1/8, okay? So we go 2, which is 16/8, 17/8, 18/8, 19/8, up to 31/8, right? So if you look at this, we keep counting up like this, and then after 31/8, which is what we have here, the next will be 32/8, or 4, okay? And then now we'd be incrementing by fourths, okay? So every time we kind of fill out the mantissa bits, okay, we got 4 mantissa bits, and every time we fill these out with 1, 1, 1, 1, okay, all ones, then at the next point, our increments increase in size. Our increments double in size, okay? So we got 16/4, 17/4, 18/4, so on and so forth, up to 31/4, okay? And then at this point, we reach 1/2, okay? And so the largest value I can represent, counting by halves, I get 8, 8.5, 9, 9.5, 10, 10.5. I keep counting, and I get to 31/2, or 15.5. This is the largest value I can possibly represent with this system, okay? After 15.5, the computer would count this as infinity, okay? Which sounds silly, but because 15.5 seems so small compared to infinity. But if you think about it, any number is small compared to infinity, okay? So even though if we have 64 bits, you can represent like a very big number in terms of human scale, but compared to infinity, it's still very shy of infinity, okay? So this is the largest number we can represent. We got 15.5. So the increment here is 1/2, and the largest value we can represent before infinity is 15.5. Anything larger than that becomes infinity. Okay? So if we think about double precision, okay, we've got 1 sign bit, 11 exponent bits, and 52 mantissa bits, okay? And so the smallest positive non-zero value has a sign bit of 0, 11 0 bits for the exponent. That puts us in denormalized mode. Okay, so the bias is 1 less than normal, so we got 2 to the negative 1022. And the mantissa would be 51 0 bits followed by a 1 bit. Okay, so that would be basically 2 to the negative 52. Okay, I think. 51 bits followed by... okay, so anyway, if I were to move this decimal place over, so if I do this, this is equal to 1 times 2 to the negative 1074. This is the smallest value I can represent. Let me make my font bigger for you guys. This is the smallest value I can represent that is not 0, okay? Anything smaller than this, if I try to do 2 to the negative 1075, will give me 0, okay? R is not able to distinguish, the computer is not able to distinguish this value from 0, okay? But this is the smallest value we can get, all right? The smallest normalized value, okay, would be 1, followed by, would be all 0 bits, and basically the exponent would be 10 0 bits followed by a 1, okay? The bias is 1023, our exponent is negative 1022. So this is 1 times 2 to the negative 1022. 2 to the negative 1022, this is 2.225. This is the smallest normalized value we can represent. This is also known as dot machine double X-min. Okay. So if you type in dot machine, this will tell you basically the smallest and biggest and smallest values that it can represent. Okay. And I didn't have time to complete all of my slides here. Okay. There's a few things and some interesting consequences. Okay. What if I did? What if I created a loop? While true. Okay, well, first of all, we're going to just start off at x equal to 0, okay? And then what if I created a loop? While true, x equals x plus 1. Okay, and I let this run, right? And so it's just adding 1 and it's counting 1, 2, 3, 4, 5, 6, 7. And I let this run for a long time, okay? And let's say my computer was super fast, and I come back, I don't know, a month later, okay? What will my computer reach? Okay, so let me, so right now my x is, I don't know, some number, okay? Dot machine double x max. Where is it? Double dot x max. Okay, this is the largest number I can represent that is not infinity. Okay, so this is basically all 1s and a 0 for the exponent. Okay, so not all 1s, but all 1s and a 0 for the exponent, and then all 1s for the mantissa. Okay, and so anything bigger than this, so this is like 2 to the 1020. 2 to the 1024 will be infinity. 2 to the 1023 is this. And so if I do 2 to the 1023 plus 2 to the 1022 plus 2 to the 1021 plus 2 to the 1020, so on and so forth, I'm going to get something that approaches this number, okay? But if I do 1 and keep adding it, it's not going to reach this number. It's going to get stuck somewhere. It's going to get stuck. All right? So I just want to kind of all right. Wait. Sorry. Okay, so let me do, okay, so here I've got y is just shy of 2 to the 53, okay? And so I just want to show you what happens when I do y is y plus 1, okay? So, okay, so if I try to add 1 to y, it's not able to do it, okay? 2 to the 53, okay? So what's going on? What's happening is that I've reached a spot, okay? So remember, every single time our bits fill out with 1s, the increment size increases, doubles, right? Okay, so we started off with increments of 64ths, then our increments reached 32nds, then 16ths, then halves, or quarters, halves, and so on, okay? We could imagine a point where our increment is currently 1, okay? And then we fill out all of those bits, and then we go to the next spot, and then our increment is 2, okay? And so if you try to add 1 to that, the computer is not able to distinguish between one value and the next value because it is smaller than the increment size, okay? And so this is something that our brains aren't accustomed to because we're accustomed to real numbers and having infinite precision everywhere. But here I'm stuck at a position where if I try to add 1, 2 to the 53 looks like this, and if I try to add 1 to this, it won't let me. I can add 2 because my increment size is 2, right? I can add 4, okay? But if I try to add 3, it can't distinguish between 2 to the 53 plus 4 and 2 to the 53 plus 3, okay? So adding 1 to it doesn't work, okay? I can add 2 because my increment size is now 2, right? And this is a weird thing. And so as the numbers get bigger, as you're reaching these huge values, the increment size might be on the order of 1,000. It might be on the order of, 2,000 and things like that. And differences smaller than that will not be distinguished by the computer, okay? And so that's how it goes. Okay, we'll end there. Have a happy Valentine's Day. Have a good weekend, and we'll see you guys Wednesday, okay?
Thank you for the candy.
You're welcome.
Thank you.